My name's Bryce. I'd like to discuss with you some of the research we've been doing here at the CSRC. We've been utilizing deep neural networks to find sufficiently accurate solutions to partial differential equations utilizing the Legendre-Galerkin Approximation. A brief overview is nonlinear differential equations are challenging to solve numerically and computationally expensive sometimes, and it's important to understanding many dynamical systems. Consider a set of differential equations where capital F is some functional and little f is the forcing function, and B is the boundary operator, and G is that function. Now, the functional f is linear or nonlinear operator, and B is the boundary operator. The main premise of our work here is, can a neural network learn a sufficiently accurate solution to a differential equation when given the forcing function? The main purpose of the Legendre-Galerkin deep neural network is to learn a set of coefficients to reconstruct the solution to the partial differential equation. We do this by utilizing the forcing function as the input to a neural network to learn an arbitrary function that is the solution to the differential equation. Once we've found these set of coefficients, we can reconstruct through the global basis function, phi, the solution to the differential equation. And then we can impose the weak form of the derivative in order to regularize our neural network and further improve the optimization algorithm in the loss function. The convection diffusion equation presents an interesting problem that is non-trivial. If we're able to solve this paradigm problem, then our method could extrapolate to two-dimensional problems or time-dependent problems. So we begin with the convection diffusion equation. As you can see here in the convection diffusion equation, our model has converged after roughly 62,000 epochs with a mean absolute error of roughly on the order of 10 to the negative 7th. The relative L2 error of this model is as well 10 to the negative 5th, and the L infinity error of this model is 10 to the negative 6th. So for a linear differential equation, we see here that we get roughly 10 to the negative 6, 10 to the negative 7th accuracy, which is very nice to see. And in the bottom left corner, you can see one of the solutions from the test data set and how our model fares. In the previous slide, we looked at the convection diffusion equation with Dirichlet boundary conditions. Here we present the Helmholtz equation with Neumann boundary conditions, where the derivative is 0 on the boundary. You can see that our model obtains a mean absolute error of roughly 10 to the negative 6th, as well as a relative L2 error of 10 to the negative 5th, and an L infinity error as well of 10 to the negative 5th. As you can see in the bottom left-hand corner, that our solution on test data, which is data that occurs out of sample and not present during training, solves this equation quite well given the forcing function. We can see that it has a nice smooth 0 derivative at the boundary. Here we present Berger's equation, which is a much more challenging problem for a deep neural network because it is a nonlinear differential equation. So we've got Berger's equation here with Dirichlet boundary conditions. And so we can see that after 25,000 epochs, that we obtain a mean absolute error of 10 to the negative 4th, a relative L2 error of 10 to the negative 4th, and an L infinity error of 10 to the negative 4th, which is quite nice. We believe that if given more time, more epochs, then this model would improve to be on the order of 10 to the negative 5th or 10 to the negative 6th with respect to the L2 error, relative L2 error. My name is Bryce Chudomelka. I'd like to thank you very much for attending this talk. We demonstrated that the Legendre-Galerkin deep neural network finds sufficiently accurate solutions to partial differential equations, given enough time, large enough data set, and that our solutions or models were on the order of 10 to the negative 5th or 10 to the negative 6th. Thank you very much. Have a nice day.